We're starting a new lecture about number families, number systems or number families. That's what we call them. Basically, numbers are everywhere around us. In every in we may not focus too much on them, but in everyday lives we see numbers constantly, right? But not all numbers behave the same way. So, for example, think about when you go and you buy yourself a book. Now, can you buy like three-quarters of a book? That's impossible, right? Can you go to the store and say, well, give me 0.35 of a book? Then would it make any sense, right? So you can buy half of a book, or you can buy a quarter of a book. You either buy one book, or you buy two books, or you buy no book at all. Okay. Similarly, temperature can be below zero. So when we say, for example, temperature, there is a temperature, for example, it says 100 degrees centigrade, but there's a temperature of 0 degrees centigrade. Is there a temperature below zero? Of course, there is a temperature of, -1 degree centigrade, all right, or -2 degrees centigrade. So temperatures can be below zero, right? Negative and -1 and -2 and whatnot. All right, money. You can divide money, right? So for example, money can be divided into, so for example, if you open your bank account, it says something like this, 7,432.15, right? So PKR, something like this. Your bank account can say something like this, right? So it allows for decimal values. So which means we have different types of numbers. Okay, so these basically, I hope you can see the difference, right? These differences lead to number families. Now, what are number families? This is a sort of a diagram or a way to represent the number families, right? All the numbers that we normally use in our daily lives, they belong to real numbers. Okay. There is another some number system which is called complex numbers, but we won't get into complex numbers right now. All the numbers that we use in our daily lives, almost, yeah, they're all real numbers. Complex numbers have a use too, but they have a very highly technical um, applications. Deep inside the number system, we have natural numbers, right? And a little outside, we have whole numbers and integers, rational numbers, and real numbers. Now, here's an important thing. They all, of course, we have irrational numbers as well. All of these numbers lie under real numbers. Okay. So if a number is a rational number, it can be an integer, it can be a whole number, it can be a natural number. Okay. So if I were to pass a statement, all natural numbers are real numbers. Yes. Okay. Are all real numbers natural numbers? Not necessarily. There may be some numbers, there may be some real numbers, which maybe not be maybe natural numbers, may not be. So that's the key idea behind. We'll take a look at each number type in a while. So let's take a look at one. We'll start from deep inside. We'll start from natural numbers, and we'll gradually move outside. Okay, so we'll start from natural numbers, then move on to whole numbers, then integers, then rational numbers, then irrational numbers, and of course, all the rational numbers and all the irrational numbers, they make up the entire real number system. What about the numbers which are not real? They're called imaginary numbers. They're also called complex numbers, but let's just call them for now imaginary numbers. Okay, so let's start from this. Let's start from natural numbers. What are natural numbers? Well, we use this alphabet to denote a set of natural numbers. Okay, this N means we're talking about natural numbers. Natural numbers are counting numbers. So for example, when we use a count, for example, the number of students in a class, right? There could be 30 students in a class. In the case of your class, there could be more than 50 students, but you cannot have 50 and a half students. You cannot have 60.3 students. Make sense? So they're counting numbers and are used to count objects. Where do they start from? It's really important. They start from one. Okay. It does not include, it includes, for example, one, two, three, four, and so on and so forth. They just keep going in a certain direction, keep going. A million is also a natural number. 2 million, a billion, a trillion, they're all natural numbers. It includes all positive integers. What are integers? We'll talk about it in a while. But what it does not include, of course, it does not include a zero, and it does not include negative numbers. Okay. Uh, It's really important to note down the difference between the natural numbers and the next we'll talk about is whole numbers is zero. Right. Examples. Well, the examples of number of students in the class, for example, they're natural numbers. Number of books on a shelf. So if you go to a library, the number of books in a bookshelf, would be natural numbers, right? You cannot have, 30 and a half book and whatnot. We can have negative three students, right? You cannot say, well, I have negative five students in my class. That wouldn't make any sense. You cannot have 2.5 books. Okay, so these are natural numbers, right? Zero, one, oh, sorry, one, two, three, four, on and on. Okay, I think this over here is really important part of that you need to know. Next, whole numbers. Whole numbers include natural numbers and they include one really important number, and that is zero. Okay, they include natural numbers and a zero. So they start from zero. But the rest are all natural numbers. One, two, three, and so on. Zero is really important. Okay, zero may not be used in counting, but it is really important. So, for example, if you have no money, you should have a number to represent, right? If you have no money, you can say, well, zero money. If you open your bank account and it says 0.00, which means you're broke. No books, for example, no attendance, they all belong to the idea of zero. So balance in the bank account. If you, for example, if you haven't made any deposit, your bank account is empty, so the balance would be 0.00 or just zero. Number of unread emails. So let's say you have read all of your emails, you open your Gmail or you open your mailbox and you read all the emails, then there are no unread emails left. So that number would also be zero. Is zero natural? Of course, zero is not a natural number. We know that. The difference between natural numbers and whole numbers is that whole numbers include a zero. Right? Next, you have integers, really important. Integers include all the positive numbers, all the negative numbers, and it includes a zero. Okay. So for example, you might start from, for example, -3, -2, or for example, you may start from -2, or let's start from -3, -3, -3, -2, -1, 0, 1, and 2, so on and so forth. It just keeps going in both directions. Okay. It keeps going in this direction and it keeps going in this direction as well. There's another way of writing integers as well. You can also write integers like um, 0. So there's, I hope you can see that there's positive one, and of course there's opposite. The opposite of positive is -1. So I can bunch them together. I can write plus minus 1, right? Plus minus 2, plus minus 3, and so on. Okay, that's a set of integers. We use z to represent the set of integers. How are integers useful in real life? So for example, let's say temperature. We can say, we just talked about temperature. Temperature can be -5, right? So it's a negative integer. Um, Negative integer. Okay. Now think about this. Think about a building, right? Um, there's a building, right? And this is the ground. Now, this would be the ground floor. This would be the first floor, second floor, third floor, fourth floor, and so on. What about the basement? Let's say there's a large basement of the building. What do you call that? Right? Let's say let's call the ground floor the zero floor. What about the basement? Right? So to represent the number of floors of a basement, you'll say, well, it's -1, and maybe let's say the basement has two floors, so -1, -2. You can think about it like that, right? Uh, Profit and loss. So profit can be represented by positive, and loss can be represented by negative, right? So loss of $20, we can say, well, -20. Okay, so this could be one of the ways to use positive and negative integers in our real lives. Then, really important are rational numbers. Now, uh, rational numbers, first of all, they can be written in the form of a fraction, a over b. Some people write it as p over q, but it really makes no difference. A over b, they can be written as fractions, but the only condition is the denominator cannot be zero. I think we talked about this in the class as well. Uh, Having a zero in the denominator is a disaster. You cannot have a zero in the denominator, right? First thing, because it's one of the danger zones in mathematics. You cannot have a zero in the denominator. Okay. And then the second condition is the top and the bottom should be integers. Okay, so I'll give you an example. For example, 4 by 7 is a rational number because 4 is also an integer, 7 is also an integer. Um, Negative 1 by 5, that's also an integer, right? 2 over 6, or maybe 100 over 100 over 7, they're all integers. Okay. Now, let me give you an interesting example. 0.5. It doesn't it doesn't look like if it's if integer, right? But if you focus on the definition, the definition says a rational number is a number that can be written as. It doesn't always have to be a fraction, but you can convert it into a fraction. Okay, so zero point 0.5, I can also write zero point 0.5 as a half, right? 1 by 2. Now, it looks like a rational number now, right? Because we have a integer on top and the integer at the bottom. Okay. So integer numbers are not always fractions, but they can be written as fractions such that you have integer at the top and integer at the bottom. Okay, so let's take a look at a few tables and let's see if they can be written as fraction form or not. So zero point 0.5, I can write it as 1 divided by 2, right? For example, I can write it as a half. Okay. 0.25, think about it, 0.25. I think we may not have discussed this, but I think I've put a video about converting decimals into fractions. So if you have 0.25 and if you want to convert it into a fraction, real quick, move the decimal point 2 points forward, or any number of points such that you get a to the last non-zero number. Okay, so I'll move it 2 steps forward. So that's going to be 25. You made 2 jumps, right? So write 100 at the bottom. That's it. Okay, let's say you have 0.256, right? How many jumps would you have to make? You'll have to make 3 jumps. So if you have to make 3 jumps, that's going to be 256 divided by 1,000, right? Let's say you have 103.29. Okay, maybe you have 103.16, right? Then you'll have to make jumps. You'll have to make jumps 2 jumps forward, right? So that's going to be 10316. You made 2 jumps, so put 2 zeros, and that's going to be 100. So you convert decimals into fractions. So 0.25, I can write it as well. If I make 2 jumps forward, that's going to be 25 over 100. Definitely a definitely a rational number. This is also a rational number. -3, I don't have to write it as a fraction, but if you force me to write it as a fraction, I can write it as -3 divided by 1. Okay. If you play, you can place a 1 at the bottom. 2.75, you can already tell you have 2.75, make 2 jumps, that's going to be 275 over 100, and of course it is a rational number. Okay, so important idea is so think about it. Let's go back to this picture and let's analyze this statement. So if the statement says all integers are rational numbers, does it make sense? Let's go back to our picture and say integers. So you have a bigger circle which has rational numbers, right? And within rational numbers you have integers. Okay, so of course all of the integers lie within rational numbers. So yes, all integers are rational numbers. The answer would be true. All integers are rational numbers. Okay, so let's take an integer. For example, let's take an integer -11. Okay, how is it a rational number? Well, if I can write it as a fraction, if I have to write it as a fraction, I'll just put a 1 at the bottom, right? And so now you can see an integer at the top, an integer at the bottom. That makes it a rational number. Okay, but here's the important part. Are all decimals rational numbers? If you see a decimal number, would you real quick classify it as a rational number? No, not all decimals are rational numbers. Okay, then you might ask the question, well, if not all decimals are fractional numbers, uh, then what are those decimals which are not rational numbers? Let's take a look at them. Decimals have two main types. One of them are called terminating decimals. terminating decimals. And the other type of decimals are called non-terminating decimals, right? Now, what are terminating decimals? Decimals which end at a certain point. Terminate. You guys are English students, you know that. What does the word terminate mean? It means to end at a certain point, right? So this decimal ends at 5. Okay, 0.25. Even if you have a decimal as long as you want. For example, if you have a decimal like 39.1375526, it's also a terminating decimal. No matter how long it is, it stops at a certain point. So if you have a decimal that stops at a certain point, it doesn't keep on going, it's a terminating decimal. Okay. Um, let's convert this into, so if you have, example, you have 7.75, you can write it as 75 over 100. Okay, this is a code. I can write it as 75 over 100. As simple as that. Okay. Then you have decimals which are called non-terminating decimals. Okay. The non-terminating decimals further divide into, um, they're further divided into uh, recurring and non-recurring. Okay. Recurring and non-recurring. I'll talk about recurring in a while. But if you have a decimal, right, that is a terminating decimal, which means it stopped at a certain point, it is a rational number. Okay. What if it's a non-terminating decimal? It doesn't stop at any point. If it's a recurring decimal, it'll be a rational. But if it's non-terminating and it's also non-recurring, that's where we have a irrational number. Okay, I'll explain this in a while. But this diagram is super important. Um, I would recommend remembering this diagram. Okay, so one more time. Decimal breaks down two types of decimals, terminating and non-terminating decimals, right? Terminating decimal further divided into recurring and non-recurring. If you have a recurring decimal, that's a rational. If you have non-recurring decimal, non-recurring, non-terminating, then of course it's a irrational number. Okay, so as we had a pretty good look at this, we saw a decimal which stops at a certain point. It can be written as P over Q. It is a rational number. Okay. Now let's talk about decimals that repeat forever. 0.33, and this keeps going on and on, right? In up until infinity, it just keeps going on and on. Is it a rational number? Now notice, is it a recurring? Yes. The recurring means there is a number that keeps on repeating. Do you see this 3 keeps on repeating? Right? So I can simply write it as 0.3, and some people put a dot on top of it. Some people put a bar on top of it. It doesn't make any difference. So there's 3 that's recurring. Okay. 0.6, I can write it as 0.6 and a dot on top, which means it's a 6 just keeps on going on and on and on. I don't have to write it like 3 times or 4 times. I could just put a dot on top of it, which tells me that it just keeps on going. This is interesting. We have a 2, 7, 2, 7, 2, 7. So we have a number 2, 7 that keeps on repeating, right? So I can write it as 1.27, and I'll put a dot on top of it. Make sense? So I want you to grab a calculator, right? And if you have a scientific calculator, that's even better. Convert 1 over 3 into decimal. Try doing that. You will get something like this, 0.33. Of course, your calculator might stop at this point, right? But in reality, it just keeps on going on and on. Okay. I'll give you a demo of how this works. So let's say if you have 1 divided by 3. 1 divided by 3 means you put 1. I'm sure you've done like long division in a childhood. Let's refresh that. So we have 3 are outside and 1 inside. Literally, the word says 1 divided by 3. So 3 is the one that divides 1. 3 is something that divides 1. 1 is smaller, so I'll put a 0. I'll put a dot. Decimal, that gives me 10. Now, if I were to solve that, 3 times 3 is 9. I'll be still left with 1. And 1 is again smaller, so I'll put another 0 over here, right? Then I'll do another 3. right? That gives me 9. I'm left with 1. I'll add another 0. Just because I've added a decimal, I can put in as many zeros as I want. But if you notice, there's a pattern that keeps on repeating itself. Every time you do a division, you're going to keep adding the same remainder. You keep on putting the zeros. The cycle never ends. It's a never-ending cycle on both sides. This is why it's called non-terminating. It is something that doesn't terminate. It just keeps going on and on. The decimal equivalent of it is 1 over 3. How do I know that? There's a long procedure behind it, which we won't talk about it right now. Okay. So idea is repeating decimals are rational numbers. I think we discussed this earlier as well. Okay, so one more time. Decimals, okay, terminating and non-terminating. Non-terminating has recurring and non-recurring. Um, if you have a decimal that's terminating, good, that's rational. If you have a non-terminating decimal that's recurring, good, that's a rational. But if you have a non-terminating decimal that's also non-recurring, then it's a irrational. Okay, I hope it makes sense. Next is real numbers. So real numbers is the umbrella term. It contains all the rational numbers and all the irrational numbers. Okay, so I think it's time that I will bring back the same diagram over here. Okay, if you notice, let me bring it over, let me bring this diagram over there to better visualize everything. Okay, so I'll bring it over here. Decimal identity, real numbers. Okay, let's put it over here. So I hope you notice, if I were to ask what are real numbers, you would say, well, real numbers are made up of all the rational numbers, because everything is inside rational numbers. Okay, so I can say all the rational numbers and all the irrational numbers. Okay, real numbers, what will be the definition of real numbers? All the rational numbers and all the irrational numbers. So when I say rational numbers, I'm covering everything. I'm covering integers, I'm covering whole numbers, and I'm covering natural numbers as well. Now, what are irrational numbers? Square root 2, for example, is an irrational number. Okay. What about square root 4? Square root 4 is a perfect square, right? So square root 4 is 2. It's not an irrational number. But square root 5 is, it's rational, but square root 5 is irrational. Okay. Square root 6 is also irrational. Square root 7 is also irrational. Square root 8 is also irrational. Square root 9 is rational because square root 9 can be written as 3. Okay, we'll talk about squares and square roots in a while, so that'll make more sense. But the idea is square roots of perfect squares. Okay, 2 squared equals 4, 3 squared equals 9, 4 squared equals 16. These numbers are called perfect squares. Okay, 5 squared equals 25, 6 squared equals 36, and the list goes on and on. Okay, these numbers are perfect squares. Any number between 16 and 25 is not a perfect square. So take any number, for example, 5, not a perfect square. 6, not a perfect square. Take any numbers between 9 and 16. 10 is not a perfect square. 11 is not a perfect square. Okay. So if you square root any of the number that is not a perfect square, you will get a irrational number. Okay. Right. Pi is a classic example of irrational number. Okay. There's a line. Let's write on a few more irrational numbers. So let's write on square root 6, square root 13, on and on. The list just keeps on going on and on. Okay. We measure many irrational numbers. We don't normally try to measure them because their values are pretty like they just keep going on and on. So instead of measuring them, we approximate them. Okay. For example, if you have something like 0.999999999, it just keeps going on, right? Instead of writing all of that, you could just write one. That's not the exact value, but that's approximation. Okay. So for example, if you go to a superstore, let's say, and or you watch an ad on your mobile phone, it says On sale, Audionic, Soundmaster, something like that, because I keep getting all of these ads. Audionic, Soundmaster, earbuds, the best in town, whatever, and only 2599. Speak here, I'm sorry, not dollars. Only rupees 2599. Am I going to pay 2599? Of course not. I'm going to pay 2600 for it. Okay, so this is an approximation. 2599, of course, is not equal to 2600. This is why I did not put an equality sign. I put this sign which is called approximately equal to, or roughly equal to. Okay. So these are all the number systems that we normally look at. These are all, I would say, not number systems. I think a better definition would be these are all the types of real numbers. Natural numbers, one more time, 1, 2, 3, 4, 5, and so on. I should write that actually. 1, 2, 3, and so on, right? Whole numbers would be 0, 1, 2, and so on, right? Integers would be 0, plus minus 1, plus minus 2, and so on, right? The rational numbers would be 3 over 4, etc. And of course, irrational number would be square root 2, something like that. Okay, I think it's too small. I'll just take it off. Pi is a classic example of irrational number. Do not forget that. Okay, let's do a real small exercise and see if a number can be more than one. So 7, we know that is a natural number, right? Is it a whole number? Of course, it's a whole number. Is it an integer? Yes, it's also an integer. It's also rational. It's also a real number. Okay. So if a number lies really at the root, natural number, it's everything. It's natural number and whole number and integer and rational and a real number. Because it's just the circles nested inside each other. Okay, 0. Is 0 a natural number? No. A whole number? Yes. Integer? Of course. Rational? Yes. Real? Of course, yes. -4 is not a natural number. We know that. It's not a whole number because whole numbers are positives and 0. Integer? Yes, of course. Rational? Yeah. If it's an integer, it's going to be rational and it's a real number. 0.125, not a natural number, not a whole number, definitely not an integer because integers are, we don't have decimals in integers. Rational, yes. Why? Because it's a terminating decimal. It's a terminating decimal. So, which means it stops at a certain point. I can write it in the form of a fraction. I can write it as 3 jumps. So that's going to be 125 over 3 jumps would mean 1,000, 3 zeros. Okay, so it is a rational. If it's rational, of course, it is also a real number. Okay, square root 5. Natural, definitely not. Whole number, no. Integer, definitely not. Rational, no. It's not a rational number because it's a square root of a number that is not a perfect square. Real, yes. Okay, because it's an irrational number. You know that. It's a irrational. Okay, so I hope you've gotten a pretty good idea of what all of these numbers actually mean. Okay, so let's classify a few numbers and let's check box or mark. Let's check our boxes. 13, not a natural number, not a whole number, not an integer, not a rational number. The reason that it's not a rational number because it cannot be written as P over Q, such that P and Q are both integers. You might argue, okay, I can write it as square root 13 over 1. Right? Would it be a rational number now? Think about it for a while. I just wrote it as P over Q. It would still not be rational because P over Q should have integer on top and integer at the bottom. Okay. So since square root 13 is not although 1 is an integer, square root 13 is not an integer. So it's not a rational number. It is irrational, yes. Of course, it's a real number as well. Okay. -5, not natural number, not a whole number. Yes, an integer. If it's an integer, of course, it's a rational number. It's not irrational because it's irrational. The number can be either rational or irrational. Okay, so be careful about that. Real, yes, because real numbers are essentially natural and rational and irrational. Okay, 2 by 3, not a natural number, not a whole number, not an integer, because you cannot have fractions in an integer. Yes, it's a rational number. Why? Because this is an integer, this is an integer. So it is a rational, but it's not irrational. You can either have it can either be rational or irrational, and definitely a real number. Negative 0.83, very interesting. Not a natural number, not a whole number. We know that, definitely not an integer. Is it rational? Let's see. Let's make two jumps forward. So it's going to be negative 83 over 1,000 because we make three because we made three jumps. Now, is it rational? Let's see. Is the top integer? Yes. Is the bottom integer? Yes. So it is a rational number. Okay. All right. If it's rational, it's not going to be irrational. It's definitely a real number. Okay. Um, Interesting. Here we go. 27. 27 is a natural number and a whole number and an integer and a rational number, not a rational number, yes, a real number. 20.6. So do you see a repetition? 47 is going to be 2.6. 47, 47, 47. The list just keeps going on and on. Natural, no. Whole number, no. Integer, no. Is it irrational? It is a decimal that is non-terminating, yes. Okay, it's non-terminating, but it's also recurring. It's a recurring because we have 4 7 that keeps on recurring, right? So as long as you have a terminating decimal or a recurring and non-terminating decimal, it is going to be irrational. So I'll check mark this. The irrational, if it's irrational, it's gonna be rational, and yes, okay, I think, yeah, all right. Next, 3.055, same case because we have a repetition, so not natural, not whole. What's this one? Not an integer for sure. A rational number, yes. Not irrational. Real number. I'll let you do the rest. They're pretty simple. I think pause your video for a while and you can do. They're pretty simple. And with this, we are done with our introduction to number families.